Okay, I heard a test for divergence. So if the series of terms, if they go to 0, then what do we know? Nothing. Okay? But if they don't go to 0, then we know the series diverges. Okay? So that's a test for divergence. We have the geometric series test. And that is so if R, your common ratio, is less than 1 in absolute value, then it converges. Telescoping series. It's not really a test, but if you can find a finite sum, then it converges. Integral test. P-test, comparison test, and the limit comparison test. Those last two we'll spend more time on today. Okay. Right now, this is our arsenal to figure out whether a series converges or not. We've got a few more tests on the way. Okay. These don't. You can't always use each of these tests. For example, the integral test only says something about it has to be positive, continuous, and decreasing. So oh man. I need like one good sneeze, and I think that would help me. But okay. Let's look at this example of I want to talk about the way we use integrals to approximate things. So here I've got 1 over n squared. I'm just going to add up the first 3 terms. Okay? But I'm going to represent it by adding up to by drawing the values, the rectangles to my right. So this is 1, this is 2, this is 3, this is 4, this is 5, etc. So the values, as I plug in n equals 1, n equals 2, n equals 3, I represented those with these blue lines, light blue lines going up and down. And I can choose to draw the rectangle on either side of those. So if I draw it to my right and I add up the first 3, then I've used those 3 rectangles to approximate the sum. I know that's not out very far. We're not very close. Okay? But I could use an integral to approximate the rest. I can fit a curve through all those points. This is 1 over x squared. Now, where would I start my integral to approximate the rest of the rectangles, the area of the rest of the rectangles in the sum? I heard someone say 4. Here, I've added up these first 3, so I have 1 over 1 plus 1 over 4 plus 1 over 9. I've added up the first 3, but from 4 on, I could approximate that with the rectangle, with the integral. And is that integral going to be larger or smaller than the sum of the rest of the terms? It's going to be smaller because I have this error. The rectangles, I've got this little piece up here on each one of them. So if I take the first 3 and add onto it the integral from 4 to infinity of 1 over x squared dx, is that larger or smaller than my true sum? It's got to be smaller than my true sum. These first three terms are exactly the same as the first three terms of my actual sum, but the rest is smaller than it. So this is going to be a smaller bound, a lower bound of our actual sum. Now, what if I draw this the other way? So here are my values. I have 1, 2, 3, 4, 5, 6, etc. But if I draw on the left-hand side now, if I draw my rectangles this way, and add up the first three, let me draw my curve in there, my integral in there. Okay. Where would I start to approximate the rest of the series? With the integral, where would I start to approximate the rest of the series? Last time we started at 4. Last time we added up the first three, it got me to here, so I went from 4 on. Where would I start here? 3. But from 3 on this way, is the integral larger or smaller than the value of the rest of the series? It's larger because I get these. I have this space in here that I don't include with this series. So the true value, is going to be smaller than the sum of the first three terms plus the integral from 3 to infinity 1 over x squared dx. Okay, so here we have a way to bound the true sum. So notice I had the first however many terms I add up are fine, and then I have the integral. If I start at one more than my sum, I get a smaller integral, and it's going to end up being smaller than the true sum. If I start at the value, if I start at n, then it's going to be larger. Okay, so why don't you guys work on calculating what my upper bound is? Okay, what is the upper bound? If I take S3 plus some integral, what's the upper bound for the true sum? Okay. So I got 61/36. Is that what you guys got? Okay. So added up my first three terms, had to find a common denominator there. I got 49/36 for that. Then calculated this improper integral, took the limit as a goes to infinity, and ended up with 1/3. This term here goes to 0. And so then you have to add 49/36 plus 1/3, get another common denominator, 61/36. Okay? All right. So that would be an upper bound. We could find the integral from 4 to infinity, add it to our 49/36. That would give us a lower bound. So yeah, you're just going to here you're going to have 1/4 instead of 1/3. So you've already done all the hard work for that. Okay. But let's move on. Okay. Real quickly, talk to your neighbor about how to do this series. How could you know whether this series converges or diverges? And if you don't know how, tell your neighbor what you think it should happen and why. Okay. So what do you think happens to this? Converges or diverges? Diverges. So some people at the front said diverges. But what is it close to? What should it behave like? 1 over n. The series 1 over n. It doesn't, like that -1 shouldn't have that much of an effect. Right? So it should be basically the same. Which is larger, this series or this series? 1 over n or 1 over n minus 1? 1 over n minus 1, the denominator is smaller, so the terms are going to be larger, and so we're going to be adding up larger values here than over here. So what do we know about, what should we be able to conclude about this series? It diverges by comparison. We know something about 1 over n. It's the harmonic series. It diverges. Or by the p-test, since p equals 1, it diverges. So this has got to diverge just by the comparison. It's larger than a divergent series. It's got to diverge. Okay? What if I had this? 1 over n plus 1. Can we use the same argument? No, it's on the wrong side. All we know is, you still think it should be close enough that those should, if this one diverges, this one should also diverge. It should be close enough. But it's on the wrong side. All we know is it's smaller than a divergent sequence. What does that tell us? Absolutely nothing. There are divergent sequences smaller than any divergent sequence you give me, and there are convergent sequences smaller than any divergent sequence. All the convergent ones are smaller. So it doesn't tell us anything. We just know it's smaller than a divergent sequence. But still, intuitively, you're like, they ought to behave the same. This is where the limit comparison test comes in. So we'll do this one quick example, and then I'll turn you loose on those 6, on the rest of those 6. So the limit comparison test. So you look at this, the limit of two terms as n goes to infinity. So that's kind of small. Look at the limit of the terms where one of these, it doesn't matter which, you have your series, the series that you're trying to test, and a series you pick. And it doesn't matter which one is which. It doesn't matter which way you make your ratio, which one you put on in the numerator, which one you put in the denominator. Okay? If that limit if it's greater than 0 and less than infinity. So this works, an and bn are positive sequences. Then, if it's somewhere in between, any finite value that's larger than 0, then what do we conclude? What does the limit comparison test tell us? They both converge or diverge. They behave the same. So either the series an and the series bn both converge, or both diverge. Okay, they're close enough that they will behave the same when it comes to their convergence or divergence. Okay, so let's do that specific example. We had 1 over n minus 1, and we were going to compare it to 1 over n. So let's do the limit comparison test. So the limit as n goes to infinity I set up my limit. I could have set it up the other way if I wanted to. I could have set it up limit as n goes to infinity of 1 over n minus 1 or 1 over n. Doesn't matter. Okay? Either way. Okay? So what's that going to equal? Well, let's do a little algebra. Okay, if you multiply the numerator and the denominator by n minus 1, then you get this, which simplifies to that. This goes to 1, that goes to 0, and so the limit goes to 1. So what do we know? So either both converge or diverge, but series of 1 over n diverges by the p-test. So series 1 over n minus 1 diverges by the limit comparison test. Yeah. Yeah. So some of you probably think about this as invert and multiply. I'm dividing by a fraction here, so I want to get it into just, I don't like all these bars here, right? So I'm trying to just write it as 1. So if I multiply the numerator and the denominator by n minus 1, these divide out, and then those multiplied together just give me that. So, thanks for asking, clarifying. Other questions about this example? Christian?
Is the inverse also true that, like, if that one we know, like 1 over n, is divergent, but they go to infinity, or, like, I guess that example, if that limit goes to infinity, does that mean that the other one is convergent?
It does not work that way. So, because we could get some that were, we could find two that were both divergent. And when we take the limit of the sequences, they would go to infinity, or both go to 0. So, or both convergent. One example is this. If you have 1 over n squared, 1 over n cubed, they both converge, right, by the p-test. But if you try the limit comparison test, you'd have 1 over n squared, 1 over n cubed. Take the limit, you're going to take the limit, you're going to end up with the limit of n as n goes to infinity, and that's infinity. But they both converge, so yeah. Good question, good question. Okay, other questions? Yes? Yeah. So, so let's talk about what tests, what series do you want to use when you're looking to compare something? Compare either limit comparison or not. The two really nice series to go to are p-tests. So things of 1 over n to the p, because they're easy to know, or geometric series, where you have, a times r to the n. So these are the places that you want to go, because they're easy to say, hey, 1 over n squared converges by the p-test. Now I'm going to use that to compare it or do a limit comparison test with that. So you might be using a couple tests to figure out where, what happens to one series. So, okay. All right, let me turn you guys loose on those problems. Oops. And I'm going to throw up one more in here. So just a reminder, this is a chance. If you have questions from the reading or questions from the videos, holler at one of the TAs, let them help answer. Okay? Yeah. If it's 0, then you chose poorly. So it's inconclusive. So you have to find something else that's closer to the series you're trying to test, so that it doesn't go to 0 or doesn't go to infinity. problems, if there are problems up there that you already know, don't spend time doing it. Start working on the ones that are going to be a challenge for you. Okay. So we're not going to, we won't be able to go through all of these. What term would you, what series would you expect to compare with this one? Either 1 over 2n or 1 over n. What do we know about 1 over 2n? We don't have a test to just look at 1 over 2n and say it diverges. But we know that that's 1/2 of the harmonic series. Okay, we can pull that 1/2 out, and then we know this diverges. And so this is going to be infinity. What's half of infinity? Still infinity. Still going to diverge. So you can't get around converging or diverging just by multiplying by a constant. So, okay. What about this one? What are we going to compare with this one? With number 2? It's the same thing. Okay, some people said 1 over 2n. Oops. Some people are going to said 1 over 2n. The question is, how do you get 1 over 2n? Okay. So the key here, one of the keys is look at the dominant terms. Look at the dominant terms in the numerator. Look at the dominant term in the denominator. And the dominant term here is this 4n squared. So that should be similar to, where am I? There we go. That should be similar to 1 over the square root of 4n squared. Right? That we think that minus 1 shouldn't make that much of a difference. And so should be similar to this, which is equal to 1 over 2n. And can you do a comparison here, or do you have to do a limit comparison? So 1 over 2n, does that converge or diverge? It diverges because it's half of the harmonic series, which diverges by the p-test. So we would this series would have to be larger or smaller than 1 over 2n. It would have to be larger to diverge. Is it larger? Yeah, the denominator is smaller. This minus 1 is going to make it smaller, so the denominator will be larger, so we can just do a comparison. So you could say this series here diverges because I can compare it to 1 over 2n, and it's 1 over 2n is smaller than 1 over the square root of 4n squared minus 1. Each of those terms are smaller, so it diverges by the comparison test. Okay? Questions? Any questions so far? Okay, how about 3? So some said compare with 1 over n squared. If you look at the dominant terms, they're n and n cubed. So n over n cubed, it's 1 over n squared. So you'd think that this would be close to 1 over n squared, and then you can do a comparison or a limit comparison test. So how about this one? What are the dominant terms here? Like, what are you going to compare this one to? I don't know if all of you got this far, so just take a minute, talk to your neighbor about number 4. How should we think about number 4? Sorry, what? Converges. All right. What are we thinking here for number 4? What's a series that should behave close to this, or you hope, that we know converges or diverges? So what's the dominant term in the numerator? 2 to the n. What's the dominant term in the denominator? E to the n. It is e to the n minus 1. So that's in the exponent right there. Okay, but e to the n is going to be close. The only difference is I've multiplied this one by 1 over e, and that's just multiplying by another. I've just divided by e. It's not going to impact whether it converges or diverges. So I could actually just use 2 to the n over e to the n if I wanted to, or I could use 2 to the n over e to the n minus 1. But what about this series here? Does this converge or diverge? Converges by what? Geometric series test, because r is 2 over e, which is less than 1, because e is a little less than 3. Okay. So now how are we going to use that to handle this one over here, to handle number 4? How are we going to use this fact right here? Okay, can we do limit comparison? If you're not sure whether which series is larger, which series is smaller, you can always just do a limit comparison test. So if you have a hard time reasoning through, or if it's just one of those difficult cases, then hey, just do limit comparison test. So let's do a limit comparison test for practice with these. So I'm going to set it up again down here at the bottom. So 2n plus 1 over e to the n minus 1. So I'm going to do limit comparison test to 2 to the n over e to the n. So the limit as n goes to infinity of 2 to the n 2 to the n plus 1 over e to the n minus 1 divided by 2 to the n over e to the n. So there's my nice big ratio of ratios. So I'm going to invert those. So I end up with 2 to the n plus 1 times e to the n over e to the n minus 1 2 to the n. Okay, let's rewrite those. So 2 to the n plus 1 over 2 to the n times e to the n over e to the n minus 1. And that first product is pretty easy. 1 minus 1 over 2 to the n. Excuse me. And that goes to 0. And then here, I can think about this as e to the n, and this as e to the n divided by e. Excuse me. So that part just goes to 1, and I just end up with e times e to the n over e to the n. So that goes to just e in the limit. So, all right, well, what did we get from all that work? What do we know now after I set up that limit? Then those series either both converge or diverge. This series and this series either both converge or diverge, and I know this series converges because of the geometric series test, because R is 2 over e, which is less than 1. So, okay. All right, questions? Yes? Can we use the p-test? So the p-test, so the question is, why can't we use the p-test on this problem? The p-test only says something about series of this form. So it has to be 1 over n to the p. So that's the only thing the p-test says something about. So if it's not of this form, we can't use the p-test. Even if it was 1 over like n3 plus 1, we can't use the p-test right here in and of itself, because that plus, these are not of the same form. Here, here I can use the p-test. Here I've got to use a comparison or a limit comparison test. So I expect it to converge, but to show that it converges, I've got to use the limit comparison test or the comparison test to 1 over n cubed. So, there. Okay, we didn't get to some of the harder ones. What about this? Anyone have any ideas on how to handle sine of 1 over n? There's no dominant terms here. What does sine of 1 over n behave like? Sorry, didn't hear you. Would you take the integral if it was sine of n, or would be sine of x? But sine of 1 over n? I don't know if we can actually integrate that. So, because here, like we know the antiderivative is sine of x, but sine of 1 over x. Someone said squeeze theorem. You'd be like, hey, you get a bound here? You know it's got to be between 1 and a minus 1, and actually you know it's between 1 and 0, because really all we're doing here, we're taking values of sine that are getting closer and closer to 0. So if this is 1 here, 1, and then a half, and etc., we're getting values that are getting closer and closer to 0 over here. So what is sine like around 0? What? Well, the values go to 0, the terms go to 0, but sine of x is about x. So I'll tell you that you guys already knew that, but you're like, I didn't know that, Brother Corey. But you guys have done this limit before. That limit as x goes to 0, and you get 1, right? Well, if you change the x's to 1 over n's, then you can take sine of 1 over n over 1 over n, and you can compare it to 1 over n. So, all right. Have a great day. And be careful with the water fountain. They'll get you.
Thank you.
Oh, yeah, go ahead.
I don't remember exactly how it worked. Partly because I didn't know how it worked back when I was using it.
Oh yeah.